Okay, so in this video we are going to discuss another type of system classification, which is known as reversible systems. Okay, so in the reversible system, what we observe is the system in the system there exists something called time reversal symmetry. Okay, so what is this time reversal symmetry? So in the dynamical system, the states will vary as a function of time, right? So even if we change our flow of time backward, okay, the system dynamics will not change. Okay, the governing differential equation will not change. Such a system is known as time reversible system. Okay, if such a time reversal symmetry exists, then it's called reversible system. Okay, now what all the so the example, one of the example is all physical laws. Okay, all physical laws except second law of thermodynamics. All physical laws shows this time reversal symmetry. Okay, so let's see in this example, which is Newton's second law, mx double dot is equal to f of x. Okay, so in this law, let's see whether this form is still unchanged even if we do this time reversal by making t to minus t. Okay, so let's say it represents a particle. Okay, x represents the position of a particle. Okay, so when we do the time reversal, okay, then the velocity of the particle will be reversed if we observe from reverse or backward timeline, right, or reverse timeline. Okay, so the velocity will be negative. Okay, whatever we observe as a velocity, that will be negative. Okay, so that's because velocity is dx by dt, and in the t, in the place of t we will put minus t, and therefore the minus will be resulted in minus x dot when we do this transformation. Okay, how about acceleration? So for acceleration we are double derivating it. Okay, so we are derivating with respect to time twice, so we will have 2 minus sign, and that will cancel each other and we will get the same acceleration. Okay, so finally what we will have is, for this form, if we do the time reversal, okay, this equation will remain as it is. Okay, it will not change. So so the symmetry exists, and such a time reversal symmetry not just exists for Newton's law, but also you could check for other physical laws as well. Okay, so now we could convert this equation into this form, right? So now let's see within this form how the when we do this transformation, how the system is being unchanged. Okay, fine. So now let's consider this equation. In this equation, let's just consider x dot. So when I do the time reversal, this x dot becomes minus x dot. Okay, and similarly y dot will become minus, okay, let's come to this y later. X dot becomes minus x dot. What about y? So y is a velocity. Okay, so y is basically a velocity, so that will also be a minus. Okay, So minus x dot is equal to minus y. That's what we will get after we do this transformation, and both the minus will get cancelled and we will regain its this form, x dot is equal to y. How about this one? This one, due to this transformation, so there will be one minus sign which will get added, okay. But at the same time, we know that y is velocity, that itself will become negative because of this transformation, and therefore we will have two minus sign, and those two minus sign will get cancelled and it will once again give y dot, okay. And here there aren't any time independence thing, so there won't be any change. So after I do this transformation, okay, there is no change. So in particular, since we consider y as a velocity, we haven't just did this one, okay. As a consequence of this, we have also done this one, okay. We have done this transformation along with this transformation, okay. So such a system, okay. So if I do this transformation and this transformation, after I do these two transformations, if the form remains unchanged, then it's a reversible system, okay. Okay, but why are we so interested in the reversible system? Say for the reversible system, okay, you have identified a trajectory for some fixed point, sorry, not fixed point, for some initial condition. Let's say that trajectory is this, okay. Now since this is a reversible system, there exists a symmetry, okay. There exists a kind of mirror symmetry, not exactly a symmetry, a mirror symmetry, okay. So so due to this one, okay, so due to this one, there exists a mirror symmetry with respect to the x-axis. So whatever the trajectory I'm observing over here, so in a mirror projection, I will observe a trajectory which is exactly like this, like a mirrored one, okay, mirrored one with respect to x-axis. Okay, but how about the direction? Because I can't just draw the line, I have to mention the direction as well, right? So in order to mention the direction, we have to use this one. So this one is giving a direction in this direction, but after we mirror it, okay, we have to use this one to choose the direction, okay. So the direction will be in the opposite direction, okay. So the advantage of reversible symmetry is that once I identified one side of the phase portrait, then all I have to do is mirror the part of that phase portrait with respect to x-axis, and then just change the direction of the phase portrait, okay. So that's how we can complete the phase portrait, okay. So in a general form, if we have a reversible system, all we have to do is we have to change t to minus t and y to minus y, and then we have to see whether this form being unchanged, okay. So for that thing, what do we need? What we need is this function f, okay. F has to be odd in y, okay, and g has to be even in y, which means if I change the sign of y, then it will be minus of f of x comma y. At the same time, if I change the sign of y in g, there shouldn't be any change, okay. So here it should be even and here it should be odd. Then I can easily say it's a reversible system, okay. Thank you.